Okay, welcome back. Good to see you for more quantum fun. I hope you like quantum circuits. We're going to be talking about them some more today. So let's get going. So remember last time we talked about quantum circuits and some essential facts about them. We talked about the importance of accuracy when we consider real physical hardware to simulate an ideal quantum circuit we're interested in. It was pointed out that it's good enough for our actual physical gates to have an accuracy that scales capital T if we want to be able to perform a useful computation with capital T gates. That is, the errors accumulate linearly with the circuit size. We talked about, for a typical unitary transformation in the unitary group of n qubits, how large a quantum circuit is needed to accurately approximate that unitary transformation. We saw the circuit size needed to be exponentially large in n to provide a good approximation for most unitaries. There's a corresponding statement about states. For most states in Hilbert space, if I want to closely approximate that state, starting with the product state, we need a quantum circuit with a size which is exponential in the number of qubits. We talked about the task of simulating what a quantum circuit does using a classical computer. And although the naive simulation requires exponentially large memory because we need to keep track of a quantum state in an exponentially large Hilbert space, we saw that by using a kind of sum over histories trick, we could do that simulation still with an exponential cost in terms of the time complexity of the classical calculation. We could do it with an amount of memory which is polynomial in the number of qubits. That is, BQP is contained in the classical complexity class P space. The decision problems we can solve with a polynomially bounded amount of memory. And we talked about the question of exact universality. And we saw that if we wanted to build up exactly any unitary acting on n qubits, that is possible using only 2-qubit gates. So if we can get pairs of qubits to interact in a precisely controlled manner, doing entangling 2-qubit gates, that's enough to realize any unitary transformation we'd ever want for any purpose. Now today I want to go a little further with the general theory of quantum circuits, and in particular, remember in our model of quantum computation, we envisioned that we don't have a continuum of possible quantum gates to choose from. Rather, there's some finite instruction set. We build our circuits out of gates chosen from a finite alphabet. One good reason to do that is because in the theory of fault-tolerant quantum computing, there's just typically a finite set of gates that can be done accurately in a way that doesn't spread errors too badly. So there's a real incentive for considering that model. And what we'll see today is that just a generic entangling 2-qubit gate, of course, a generic gate is entangling, is enough for universal quantum computing. It's enough for us to be able to approximate accurately if we build a circuit out of such gates, any 2-qubit unitary, and that in turn means that we can build up any n-qubit unitary. And I also want to talk about how expensive it is to simulate one set of universal quantum gates with another. Let's say we have a universal set of gates which are 2-qubit gates, and at least I have such a computer, and you have a different computer with a different instruction set with a different set of universal 2-qubit gates. And if I want to simulate what your computer does, I would like to build circuits out of my gates that closely approximate each one of the gates in your alphabet. And we'd like to see how large a circuit I need to do that. So let's start with this question of understanding how to get universality out of a finite alphabet. Of course, the unitary transformations form a continuum, so we can't hit everyone on the nose from any finite circuit of finite size because there are only a finite number of such circuits if the circuit size and the alphabet of gates are finite while there are an infinite number of unitaries. So the task we want to consider is accurately approximating any unitary. So let's say we have little n qubits. We're considering transformations that are unitaries acting on the 2 to the n dimensional Hilbert space. Here I said SUN, SU meaning determinant 1. The point being just that I don't really care about the overall phase. So let's say there's some target unitary which has determinant 1. And then what I want to do is find a circuit built from my gates, this alphabet of putatively universal gates, which approximates in the sup norm, or whatever your preferred norm is, but sup norm will be good enough for us, approximates with an error at most epsilon that target unitary, or I'd be okay if I get the target unitary with some different overall phase, since I don't really care about the overall phase. So really what we want from our universal gate set is to be able to realize with circuits of finite size a dense subset of all the unitaries. Dense meaning that for any element of SU 2 to the n, I want there to be some finite circuit which gives me a unitary. The circuit provides a unitary which is within distance epsilon of that specified target unitary in the unitary group. So let me first describe a simpler instance of such density. Let's suppose I'm just considering a rotation on the Bloch sphere about the z-axis by an angle which is an irrational multiple of 2 pi. I wrote it as e to the 2 pi I alpha, where alpha is an irrational number times z, the Pauli operator z. And let's consider the powers of that gate. So I have this one rotation about the z-axis, and I can apply it any number of times I want, any positive integer number of times, k equals 1, 2, 3, etc. So I claim that actually gives me a set which is dense in the rotations about the z-axis, that I can come as close as I want to any rotation by any angle about the z-axis by taking some suitable power k, applying my gate e to the 2 pi I alpha z, altogether k times in succession. Well, you can see this is really equivalent to the following question, because the rotations are compact, because e to the 2 pi I z is equal to the identity, since z has eigenvalues plus and minus 1. The rotations are equivalent to a circle. You can think of that as a periodically identified unit interval. And so the points that I can realize, the different rotations, are multiples of alpha, this irrational number, by the integer k, but modulo 1, okay? Because, when I rotate by 2 pi, I'm back to the identity again, and I just want to know how much additional rotation I have beyond 2 pi, or equivalently here, I'm only interested in the non-integer part of an integer, alpha times k modulo 1. And now I claim, first of all, that because alpha is irrational, all that the points I can get on the unit interval by considering multiples of multiples of alpha and then subtracting away the largest integer smaller than alpha k, these are all distinct. How do I know that's true? Well, suppose it's not true. Suppose that there are two values of k and k prime, such that alpha times k and alpha times k prime modulo 1 are the same, or in other words, alpha k is equal to alpha k prime plus some integer. Well, if that were true, then if k is not equal to k prime, then that means alpha is that integer divided by k minus k prime, which is a rational number. But that contradicts my assumption that alpha is actually irrational. So because alpha is irrational, we never hit the same number twice as k goes over all the positive integers. Now that means that once k gets large enough, we're going to have to come close to a point in the unit interval we've hit before. That is, say a capital K times epsilon is greater than 1, then I claim there have to be two integers k and k prime no larger than k or less than k, such that the difference between k alpha and k prime alpha mod 1 is less than epsilon. So why is that? Well, just picture the unit interval, and if it's not true, then for every point that we've hit as k and k prime range up from 1 to capital K, every point is always at least distance epsilon away from another point. So that means I can consider an interval around each point of width epsilon, epsilon over 2 to the right and epsilon 2 over 2 to the left. And all those intervals have no intersection, but there just isn't room for all those intervals, because if there are altogether a capital K of them and each one of them has width epsilon and the length of the unit interval is just 1, they won't all fit. So they have to start to overlap at some point. So once there must be a pair of integers, both less than capital K, as long as capital K is greater than 1 over epsilon, so that k alpha and k prime alpha modulo 1 are within epsilon of one another. And now I can take k minus k prime alpha, and I can multiply that by some other integer. And that means I'll get a set of points on the unit interval which are successfully less than epsilon apart. And if as I let that integer range from, well, as large as it needs to, I get a set of points which have such that the intervals around them of width epsilon completely cover the unit interval. Okay, so there won't be any gaps left. And so that means that every point in the unit interval at that point is within distance epsilon of k minus k prime alpha times some suitable integer. And that's what I mean by density. It means that for any point on the unit interval, there's some integer such that the integer times alpha mod 1 is less than distance epsilon away from that point. Okay, the multiples of epsilon mod 1 are dense in the unit interval. By the way, it might take quite a while to get to the point we want, because it might be that k minus k prime alpha modulo 1 is something really small, like 1 over Google or something. And then we might have to go to a large value of that integer to get to the point we want, but we can always do it eventually. Now, actually, we're sort of hampered here because we're just considering powers of one gate and they all commute with one another. We can navigate around the unitary group, and this we're just navigating around U1, but in the case of a non-abelian unitary group like U2, the unitary is acting on a qubit, if I have a pair of non-commuting gates, then I can get where I want to go in SU2 a lot faster. And the reason is that there are a lot more circuits I can construct. When the gates commute, then the order of the gates doesn't matter. And the only thing that matters here is the integer k, the number of times I applied our fundamental unitary. But if the gates are non-commuting, then the number of circuits I can build with altogether k gates becomes exponential in k, because I can choose any order of those guys that I want. And that means I have a lot more power when it comes to getting around U2. But even in the abelian case, even if we're just doing rotations about the z-axis, as long as it's a generic rotation by an irrational angle, an irrational multiple of 2 pi, then we'll have density in the unit interval, or equivalently in U1, the rotation group around a fixed axis. There's a similar thing I can say about a unitary that's generic in the case of an n-dimensional space. So now it's an n by n unitary, and I can always go to the basis in which it's diagonal, and the eigenvalues are all complex numbers of modulus 1, so I can write them all as e to the 2 pi I times alpha j, where j equals 1, 2, 3, etc., up to capital N. Now, generically, remember, because rational numbers are a set of measure 0 in all the real numbers, generically, all those alpha j's are going to be irrational numbers, and not only that, all ratios of the alpha j's will also be irrational. So when I start taking powers of u for any generic u, then I'm going to cover uniformly, or get density in each one of n unit circles associated with the powers of each one of these n eigenvalues. And furthermore, I can get any combination of rotations about the n different directions in the unitary group, or in other words, with powers of generic unitary, I can come as close as I want to any element of the unitary group which is diagonal in this same fixed basis. Or in other words, I can get as close as I want to any element of the form e to the I theta 1, e to the I theta 2, dot, 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 up to e to the I theta n. So a generic unitary, in the case of UN, the unitary is acting on a capital N dimensional space. If I start taking powers, I can get as close as I want to any element of U1 to the N, that is, any element of this form, as long as that's a generic unitary and all of the angles are relatively irrational, as is the case for a generic unitary. Okay, but that's, again, the abelian case. The non-abelian case is more interesting. Well, we'll get to that in a minute. Well, I guess we're getting to it now. So now suppose I have two unitary transformations, and remember, I can always write a unitary transformation as the exponential of I times a Hermitian matrix. So the remark I just made, or a special case of the remark I just made, is that if those matrices are Hermitian, meaning all the, sorry, they are Hermitian. If e to the IA, the unitary matrix, has the property that all of its eigenvalues are irrational, e to the I theta, where theta is an irrational multiple of 2 pi, then and furthermore, the eigenvalues are relatively irrational, then by taking powers of e to the IA, I can certainly get any unitary operator of the form, well, here I wrote e to the I alpha a, but now I just mean alpha can be any real number. And likewise, I can get any operator of the form e to the I beta b by taking powers of e to the IB. So it's often convenient to think about the unitary transformations in terms of their corresponding Lie algebra. The Hermitian matrices, which, so to speak, generate the unitary elements, which can, the ones which are exponentiated to get unitaries. So here we're just saying that you can think of that space of generators as being like a linear space. If in the case of the things that we can reach, in other words, get arbitrarily close to, if e to the IA has that property, or in other words, if A is such a generator, then so is A times a real number. Hence, if e to the IB is such a unitary, if B is the generator of a unitary in our set, then we can get as close as we please to B times any real number as a generator, or e to the I beta B as a unitary. And not only that, we can not only take these generators and multiply them by real numbers, we can also take linear combinations of them. So that if A is a generator of a unitary in our set of gates, and B is also such a generator, then it's also possible for us, if they're generic, if A and B are generic, to get as close as we want to e to the I times any linear combination of A and B. Okay. Forget about alpha and beta for a minute. Well, no, I guess I didn't forget about them. Here they are. Okay, that's fine. So think about it this way. So I've already told you I can get as close as we want to e to the I alpha A. That's also true of any multiple of e to the I alpha A. So let's consider e to the I alpha A, where n is a very large integer, and e to the I beta B divided by n. I think I forgot to say divided by n. E to the I alpha A divided by n, where n is a large integer, and e to the I beta B divided by n, where n is a large integer. Take the product of the two, and then take that product and raise it to the nth power, and then let n get really, really big. And then we can ask, what unitary does that get close to in the limit of very large n? So I'm considering matrices A and B, which have bounded norm, so it's perfectly fine to expand the exponential in power series. And when I do so, when I expand e to the I alpha over n, I'll get 1 plus I over n alpha A, that is e to the I alpha A over n. In the leading order, I get 1 plus I over n alpha A, and then higher order terms, which are of order, which are of order 1 over n squared. Likewise, for e to the I beta B over n, I expand that exponential. I get 1 plus I over n beta B plus higher order terms. And then I raise that to the nth power. And now I know that the limit of 1 plus x over n raised to the nth power is e to the x. That's true for matrices, just like it is for numbers. And so when I take the limit, I just get the exponential of e to the I alpha A plus beta B, as shown here. So that means that once I have a unitary in my gate set that's e to the I A, or gets very close to e to the I A, and the same thing for e to the I B, that'll also be true for e to the I alpha A and e to the I beta B if A and B are generic. And then by constructing circuits like this, in which A and B alternate many times, that means I can get as close as I want to e to the I alpha A plus beta B. So in the Lie algebra language, if I think of the generators of the sets of unitaries that I can reach, if A is such a generator and B is such a generator, then so is alpha A plus beta B. So the generators really form a linear space. They form a vector space. And they're closed under more than just taking linear combinations. They're also closed under commutation. So I claim that it will also be the case if I can reach e to the I A and e to the I B, both are generic, then I can reach e to the I gamma commutator of A with B for any gamma. Okay, so how do I see that that's true? Well, now I consider constructing a circuit like this. First of all, I guess I forgot about I didn't bother with the alphas and betas here. You can imagine those are just absorbed into A and B at this point. But the point is that if I know how to reach e to the I alpha, I can reach, sorry, e to the I a, I can reach e to the I times any number if a is generic. So in particular, I can consider getting as close as I want to e to the I a over the square root of n and e to the I b over the square root of n. From those guys, I construct a circuit in which I alternate e to the IA over square root of n, e to the IB over square root of n, e to the minus IA over square root of n, e to the minus IB over square root of n. You know, if I can get any multiple of A, if I get positive multiples, I can get negative ones too. And then I take that and I just repeat it n times. Okay, so I'm taking the nth power of this product of 4 unitaries. Now I consider again n to be very large, so I can do my power series expansion. And now we have to keep track of a lot of terms. So let's do that. First of all, there are terms coming from when I expand the exponential of e to the IA over square root of n, e to the IB over square root of n, where a hits b here. There's a minus sign because of the two i's. There's a 1 over n because of the two 1 over square root of n's. And so that's going to give me this term. I have 1, of course, which is the leading term, plus in order 1 over n. Oh, I forgot to take it to the nth power. Oh, that's okay. But the whole thing should be taken to the nth power. So I just get 1 over n times minus ab from this term of order 1 over n. And of course, there are terms which are higher order in 1 over n that I haven't indicated here. That's where the minus AB came from. It came from this IA hitting this IB. Well, I can also expand. Well, when I expand, I get the term where IA hits minus IA, and that's going to give me, multiplied by 1 over n, this a squared term. And then I can have this IA hit this minus IB, and that's going to give me this plus AB. And I also have this IB hitting this minus IA, and that gives me the plus BA. And then I have IB times minus IB, and that gives me plus B squared. And then I guess I have one more minus IA times minus IB, and that gives me the minus AB. But then I get additional terms from expanding each one of the exponentials to quadratic order. So that's going to give me, when I expand e to the IA over square root of n to quadratic order, there's a term which is minus 1/2 because the I gets squared, a squared times 1 over n. So here's the 1 over n, which I took out in front. And I have such a term, minus 1/2 a squared from expanding this exponential, plus b squared from expanding this one, plus a squared by expanding this one, and plus b squared by expanding this one. And now we notice there are a lot of nice cancellations, because here I have a squared, and here I have multiplying 1 over n, and here I have minus a squared, and here I have plus b squared, and here I have minus b squared. And then I have a minus AB and I have a plus AB, but then I'm left with a BA minus AB. That's just the commutator of BA and AB. I flipped the sign here, so I wrote it as minus 1 over n and wrote the commutator as AB minus BA. And then the other terms are higher order because they come from higher order terms in the expansions of the exponentials. Like, for example, if I expand the exponential of e to the IA over square root of n to cubic order, there will be a term which is of order 1 over n to the 3/2. And now remember, I'm taking this whole thing, raising it to the nth power. And when I do so, again, I can use the formal limit property that 1 minus x over n raised to the n is e to the minus x. And so this becomes e to the minus the commutator of a and b. So what I'm saying is, if that we can come as close as we want to A and we can come as close as we want to B, we know how to construct a circuit like this, which was going to come as close as we want to the commutator of A and B, or what I just said was really a shorthand for saying that the exponentials, which are the unitaries of e to the IA and e to the IB, are in our repertoire. We can come arbitrarily close to them. And then that will also be true of e to the minus the commutator of a and b. Remember, if a and b are both Hermitian, then their commutator is anti-Hermitian. In other words, I can write this as I times something that's Hermitian. So this is e to the I times a Hermitian operator, which is a unitary, as it must and should be. So for example, let's suppose I have two elements of SU2, which are both generic, nothing special about them. They're any elements aside from some set of measure zero, which are special. And generically, of course, they won't be commuting. And just building circuits out of those guys will be enough for me to get as close as I want to any element of SU2, to get anywhere on the block sphere, if you like, starting from some initial state. So I can write one of the unitaries if I write it in the basis in which it's, I choose the Z basis to be the basis in which it's diagonal, then it's just going to be e to the I Z times some number. So we can think of alpha Z as being a generator. The other guy doesn't commute, so it might have a component along the Z direction on the block sphere. And then there's some component orthogonal to Z, and I can line up my axes so that's actually proportional to X. And so the generator of the other element is going to look like beta Z plus gamma X. And now I know I can also get as close as I want to the commutator of the two. And the commutator of the two is going to be proportional to Y. Generically, alpha, beta, gamma are all irrational. So is the product of alpha times gamma. And so this means that from the commutator, I can build up any rotation I want about the y-axis. And a general unitary in SU2 can be written as the exponential of a linear combination of x, y, and z, because a general Hermitian operator can be written as a linear combination of x, y, and z. So from our property of closure under addition or undertaking linear combinations and closure under multiplication, we see we can get as close as we want to any unitary. We have density in the single qubit unitary group, SU2. Now, the same kind of idea can also be applied to SUN for larger n. We're particularly interested in SU4 because I want 2-qubit gates. I want to get as close as I want to any 2-qubit gate. We know the 2-qubit gates are exactly universal. So if I want density, I want to be able to get as close as I please to any element of the 2-qubit unitary group, that's SU4. The Hilbert space of 2 qubits is 4-dimensional. And if I can get as close as I want to any element of SU4, because I don't care about that overall phase, then I can build circuits from those guys to get as close as I want to the unitary acting on n qubits, right? Now, that group SU4 actually has 15 generators. In other words, the space of 4x4 traceless Hermitian matrices, traceless because I'm talking about SU4, the determinant is 1. That's the analog of X, Y, and Z, but for SU4 instead of SU2, instead of 3 generators, there are then going to be 15. But what's going to happen is if you choose 2 elements of that SU4 Lie algebra, 2 generators, and then you take commutators, and then you take commutators with the commutators, and commutators with the commutators with the commutators, and so on, as you build up longer and longer strings of nested commutators, there's no reason why you won't fill out the whole Lie algebra. The only way that could fail would be if somehow those nested commutators eventually close on some subalgebra. We don't get all of the Hermitian matrices, but just some subalgebra of them. That's not generic. That only occurs for some set of measure zero of the possible generators. So really, if I have 2 elements of SU4 and generically they won't be commuting and they're generic elements, start taking commutators, I can generate the whole Lie algebra. That means that I can get as close as I want to any unitary. Here's another way of looking at it. I already told you that if you just take a generic element of SU4 and you start taking powers of that, then that's going to be dense in U1 cubed. In other words, I'm talking about SU4, that's why it's U1 cubed, not U1 to the fourth. There's an extra overall U1, in other words, which I'm not paying attention to now. And so suppose you have two such elements, two generic elements of SU4. They're not going to commute. They won't be diagonal on the same basis. So powers of one of them generates, or is dense in, gets as close as you want to any element in U1 cubed. And powers of the other one gets as close as you want to any element of a different U1 cube associated with a different basis. And there just isn't any subgroup of SU4 that contains those two non-commuting U1 cubes. And so the only thing that can happen, the only group you can get by multiplying these elements together, and they are a group, of course, because you can multiply them to get new unitaries, and they all have inverses. The only group you can get is all of SU4 once you've got those two U1 cubes, okay? So that's already enough to see that if you take two generic elements of SU4, circuits constructed from them are going to give you all of SU4. And you can also say this, suppose I just have one unitary, one generic unitary, but I'm applying it to two qubits and call the qubits 1 and 2. Well, I can apply it to qubits 1 and 2, but suppose I apply it in the other order. I kind of change the names of the qubits and I apply it to qubits 2 and 1. Well, that's the same unitary, but it's now just being applied the opposite order of the qubits. If you can do one, there's no reason why you can't do the other. Or another way of saying it is if I swap the two qubits and then do U and then swap again, I get some other unitary, and generically it's not going to commute with the original unitary U. V and U will be non-commuting. So just by conjugating by the swap, given one generic unitary, I get another unitary that it doesn't commute with, and now with those two unitaries, I'll be able to generate everything in SU4. So in fact, just one generic 2-qubit unitary, an element of SU4, if I can apply it in either one of the two orders, that's enough for me to get density in SU4, to get as close as I want to any 2-qubit gate. And because we already know the 2-qubit gates are exactly universal, that's enough to tell me I can get as close as I want to any unitary acting on n qubits. So that's the story for generic gates. Universality is extremely typical. It's hard to avoid it. Only by choosing very special sets of unitaries do you, once you have an entangling 2-qubit unitary at all, can you avoid having a universal set of gates. Which is not to say that if the gates are non-generic, that universality can be missed, can be evaded. For example, although it's true that if I have two generic elements of SU2, that's enough to generate everything in SU2. A non-generic choice might, for example, be the Hadamard transformation. You remember that one? We've talked about it before. It's the one that flips the X and Z axes. And the matrix X, or rather S, which is a 90-degree rotation about the Z-axis, which for some reason I called P on the homework, but most people call it S, so that's what I called it here. Those don't commute. So they generate a non-abelian group, but it's not the whole unitary group. It closes on a finite subgroup of SU2. It turns out to be the symmetry group of a square. Well, that kind of makes sense because a 90-degree rotation is a symmetry of a square. And the Hadamard, actually you can think of as, because it interchanges the X and Z axes, it's a rotation about a diagonal through the cube, which flips the x and z axes. And so those are both transformations that map a square to itself. And when you compose them, you always get transformations that map the square to the square. In other words, the symmetries of the square. That's equivalent, by the way, to the symmetries of the octahedron. The octahedron and the square have the same symmetry group. They're sometimes said to be a dual polyhedra. In fact, the finite non-abelian subgroups of SU2 are all well known. They're the symmetries of the so-called Platonic solids, the regular solids in 3 dimensions, the square and the octahedron. And we can also consider the dodecahedron and the icosahedron, which are also a dual pair. And that's it. So if your gates, which are non-commuting, don't close on those non-abelian groups, there's also the group of the tetrahedron, of course, but if it doesn't close on the symmetry group of one of those Platonic solids, it's going to be dense in SU2, okay? It turns out that with that Hadamard and a rotation about the ZX by 45 degrees instead of 90 degrees, there's no Platonic solid preserved by both those transformations, and that actually gives you density in SU2 if you build circuits out of those 2 non-commuting gates. All right, so far we've been talking about reachability. As you've seen, I've given you rather hand-waving arguments, and I'm not going to be any more precise about that today, but I hope I've given you a good taste of what it takes for a set of gates to achieve density in the unitary group, and that's a very generic property. Well, now I want to talk about not just whether we can get as close as we want to some target unitary transformation, but also how large a circuit it takes to get there. What's the complexity of approximating some unitary? How large a circuit does it take to get a good approximation to some specified element of the unitary group? And we're going to see that there's a nice algorithm that tells us we can do that pretty efficiently. Once we have a set of gates, which will necessarily be non-commuting, which form a fine enough net in the unitary group. So what a net means is that I'll say an epsilon net of, it's a finite set of unitary matrices, elements of UN, unitaries acting on an n-dimensional space, such that every element of UN is within distance epsilon of some element of that finite set. I called it a repertoire here and denoted it by script R. And now I'm going to be interested in taking such an epsilon net and making a finer net by composing circuits of the elements of the net. So you can think about it this way. Suppose I have a couple of non-commuting elements of a unitary group. Let's say SU2, like the example I just gave. Let's say it's the Hadamard and the T gate, the rotation by 45 degrees about the z-axis. And then I start building circuits out of them. And different circuits are going to generate different elements. And after a while, I have circuits which are not very long. And I'm going to have an epsilon net because there's no reason why I wouldn't get one. Because of density, we know we come as close as you please to every element. So for some epsilon, which isn't terribly small, I can get an epsilon net by composing rather small circuits. I could just generate them randomly until I get the epsilon net. It won't take long. But now I want to know what it takes to get a much better net. You know, I would like to get, maybe my original epsilon net has epsilon equal to 1/10 or something, but I'd like to get epsilon equal to 10 to the minus 8. Okay. Well, if I just start generating random circuits, it'll take a long time. I'd like to have a much more efficient way of doing it. And that's what I'm going to describe an algorithm due to Solovay-Kitaev for finding such a good approximation once you have an epsilon net. And the way the argument goes is we carry out the procedure of getting better and better approximations recursively. And the key claim is this. So suppose I have a repertoire, which is an epsilon net. Then I claim that, oh, there's another important thing I don't want to forget to say, and that is this repertoire has the property of being closed under inverse. The argument that I'm going to give is going to require that. So that means that if any unitary is an element of R, then so is its inverse. Now, of course, in the case of the example I gave, the Hadamard and the T-gate, that will be easily satisfied because the Hadamard is its own inverse, h squared is equal to the identity, and the T-gate has the property, since it's a 45-degree rotation about the z-axis, that if you repeat it, it's a rotation by pi over 4, you repeat it 8 times, and you get a rotation by 2 pi, which is actually for a qubit, that's the same thing as -1. So up to an overall phase, it's the identity. And so in other words, the inverse of the T-gate is just doing the T-gate 7 times. So that's certainly we can include that in our repertoire once we have the T-gate. And then we can start making circuits out of the H and T gates. And the inverses of all of them will be in our repertoire, since the inverse of T and H are in the repertoire. And now I've got R, and it's an epsilon net. And now I want to build circuits out of the elements of R, which give me a finer net, give me a better approximation to any element of the unitary group. And so I claim the following thing, that it just takes circuits of size 5, constructed from the gates in the original repertoire, R. Those circuits I'll call a new repertoire, R prime. These will also be closed under inverse, if the original ones were. I guess that's clear, because I can take, since I have inverses of all of the gates, I also have inverses of all of the circuits of such gates of size 5. But the key thing is that this is an epsilon prime net, where epsilon is of order epsilon to the 3/2. So if epsilon is small, epsilon prime is going to be smaller. Well, actually, there's some constant c, and we won't try to work out exactly what it is. But the point is that it's a constant. So once epsilon is small enough, epsilon prime will be smaller than epsilon. And we'll have a finer net using the circuits of size 5 constructed from the repertoire than the net that we began with. So I'm going to show you that in a minute, that it is possible to get an order epsilon 3/5 net from circuits of size 5 from the original repertoire. But let's first see what it implies. The important thing is that we can do it recursively. Once we have a way of making the error smaller, we can do it again. With the new epsilon prime net, I can construct circuits of size 5 out of those, and I can get an epsilon prime prime net, and that's going to have an even smaller error. And I can keep doing that. Okay, so I guess that's what I was saying here. I do, however, have to assume that the original epsilon is small enough, and how small is small enough depends on the value of this constant. So I'm going to say, all right, we're going to start our recursive procedure with an epsilon 0 net, and I'm going to ask epsilon 0 to be less than this constant 1 over c squared. Okay, so what this claim says is that if I construct circuits of 5 gates from the repertoire R0, that's going to give me an epsilon 1 net, and epsilon 1 will be c epsilon 0 to the 3/2. I can write that as c squared epsilon 0. Oh, that doesn't look right. Oh, yeah, that's right. To the 1/2 times epsilon 0. So under my assumption that epsilon 0 is less than 1 over c squared, this is a number less than 1 multiplying epsilon naught. And so epsilon 1 will be strictly less than epsilon naught. And I have my finer net. And then I just keep doing that. I construct epsilon 2 as circuits of, I construct R2 circuits of size 5 from repertoire R1, and that's going to be an epsilon 2 net with error c epsilon 1 to the 3/2. and so on. So in other words, in each step of this recursive procedure, after we've done it k times, I'll have an epsilon sub k net where c squared epsilon sub k is c squared epsilon k minus 1 raised to the 3/2. This is the same thing as what I wrote here, because c squared raised to the 3/2 is just c cubed, and then if I divide by c squared, that's the same thing as saying epsilon k is equal to c epsilon k minus 1 to the 3/2. But I like writing it this way because that makes it particularly easy to see what happens when we recursively iterate this procedure multiple times, because each time what happens to epsilon is that the c squared we had on the previous round gets raised to the 3/2 power. So after I do that k times, c squared epsilon 0 gets raised to the 3/2 power, altogether k times. So in other words, it gets raised to the power 3/2 to the k. So the error that I have after applying this recursive procedure altogether k times is doubly exponentially small in k, okay? Because I have this small number here, less than 1, and it's getting raised to a power which is exponential in k. That's really the key point. The error is getting doubly exponentially small in k. The circuit is also getting larger. The recursive procedure is going to blow up the size of the circuit by a factor of 5 every time I go from level k minus 1 to level k, right? Because I need a circuit of size 5, the next level down to get the repertoire at level k. But that circuit size is increasing only exponentially. Compared to whatever the original circuit size was that I needed to get the original epsilon 0 net, the circuit size for level k of the hierarchy relative to that initial circuit size will just be 5 to the power k. But look, if I take logarithms of both sides here, I have 3/2 to the k equals the log of 1 over c squared epsilon k divided by the log of 1 over c squared epsilon 0. Well, I could have written this as log of c squared epsilon k instead of 1 over, but that's a negative number because it's the log of something less than 1. So I just have a negative number in numerator and denominator here that I divided out and wrote it as the log of a positive number. So what that means is that this blow up in the circuit size when I go to level k, which is 5 to the k, of course, that's 3/2 to the k raised to the power log 5 over log 3/2 in whatever base logarithm you prefer. But now if 3/2 to the k is equal to this, then it's just the log of 1 over c squared epsilon k divided by the log of 1 over c squared epsilon 0 raised to a power log 5 over log 3/2. So that's just a number. It's about 3.97. So what does it mean? It means that if I want to achieve some accuracy epsilon in my approximation, building circuits out of the original repertoire, the circuit size that I need is increasing only polylogarithmically with 1 over epsilon, where epsilon is the error. Just some power of a logarithm of 1 over epsilon is the cost in circuit size for getting that approximation. What made that work is that the approximation gets doubly exponentially better as we increase k, the level of the recursion, whereas the circuit size is increasing only exponentially. So it remains to show the claim. I have to convince you that I can really do this. Okay. So we can say the following thing. Consider any unitary in UN. That's our target. And we want to approximate it with a very small error. Well, first of all, because we have a epsilon net to start with, there will be some element of our repertoire which is epsilon close to the target unitary. in the soup norm. That's the norm I'm going to consider. We've seen that it's a useful norm for considering the accuracy of unitary gates in our previous discussion of how errors accumulate. Now I can equivalently write this as the soup norm of u tilde inverse minus identity is less than or equal to epsilon. That is, u being close to u tilde is the same thing as u tilde inverse being close to 1. All right. So now what I'm going to do is here I've got something which is close to the identity. And I would like to find a unitary which I can construct as a circuit from my repertoire, which is close to this u tilde minus 1. Okay. Now, this guy is already close to the identity and deviates from the identity by only epsilon. So the w that I'm looking for is also small, and I'm going to take advantage of the smallness of w and of u tilde inverse to do an expansion in that small number epsilon when I consider the unitary. So in other words, I'm going to be able to write them as the exponential of a unitary, the unitary will be the exponential of a Hermitian operator, where that Hermitian operator in the soup norm is epsilon small, right? Because when I expand the unitary in a power series, I get 1 plus IA, 1 plus order epsilon, plus higher order in epsilon. And so once the unitary is close to the identity, I can write it as e to the I a, where a has a small soup norm. Okay. So what I want to do is find the w we're looking for, which is going to give me a good approximation to u tilde inverse. And in fact, I'm going to construct such a w as a circuit of gates in our repertoire, which is a circuit of length 4. Okay. And that'll be good enough, because this is the same as saying that u minus w u tilde is epsilon prime close to u if I was able to find w such that u tilde inverse minus w is less than or equal to epsilon prime. So this is my goal. If I achieve that goal, then I have this. But now w u tilde is something I know how to construct. U tilde was in the original repertoire. W is going to be a product of 4 elements of the repertoire. So w u tilde is a circuit of 5 elements in the reservoir. So that's what I wanted to show. So what's missing is I have to show you how to find w, which is epsilon prime close to this unitary, which is epsilon close to the identity, where epsilon prime is order epsilon to the 3/2. That's where we make the improvement in the net, that we are able to go from epsilon, the distance this guy is from the identity, to epsilon prime of order epsilon to the 3/2, how close w is to this guy, right? And now I just have to do some, well, you'll see what I do. All right. So remember, I'm trying to find a w, which is e to the IA, where a is of order epsilon. Okay. Sorry. I want to find w, which is close. What did I mean by this? Okay. All right. To find w, I see. To find w. Here's how we find w. All right. U tilde inverse, I'm going to write as e to the IA, because this is epsilon close to the identity. I can say a is order epsilon. All right. Now, one thing's for sure, for any a which is order epsilon, I can find, maybe I have a lookup table for this or something, a Hermitian pair, a pair of Hermitian operators, which are both of size epsilon to the 1/2, such that their commutator is equal to minus IA. And so A is something that, let's say we know precisely, and so there's some B and C, which in principle I can know precisely, such that their commutator is equal to minus IA, and because A is order epsilon, and this is order BC, I can choose B and C to be of order epsilon to the 1/2. Okay. Now, because our original repertoire is an epsilon net, that means that e to the IB is epsilon close to some element of the repertoire, which I'm going to call e to the I B tilde. E to the IC is epsilon close to some e to the IC tilde, which is in the repertoire. Okay. And these unitaries being epsilon close, if I expand the unitaries, that's the same thing as B minus B tilde being order epsilon, and C minus C tilde being order epsilon. Okay. Now we use the important property that the repertoire is closed under inverse. I will construct W as e to the I B tilde, e to the I C tilde, e to the C tilde. These guys are all in our repertoire. And because it's closed under inverse, if e to the I B tilde is in it, so is e to the minus I B tilde. If e to the I C tilde is in it, so is e to the minus I C tilde. But here's the key point. The terms of order epsilon here, or the terms of order epsilon to the 1/2, cancel, because B tilde is order epsilon 1/2, but I have a minus IB tilde and a plus IB tilde, so those guys cancel one another. And I have an IC tilde, which is order epsilon to the 1/2, and a minus IC tilde, which is order epsilon to the 1/2, and those cancel one another. And so the leading terms which survive when I expand things out are the commutator of B tilde with C tilde, plus terms which are higher order come from expanding the exponential to higher order in B tilde, C tilde, B tilde, and C tilde. This is the only term of order epsilon there is, and there's no term of order epsilon to the 1/2. Okay, and what was essential was that because of closure under inverse, I could get an exact cancellation of the order epsilon to the 1/2 errors between the unitary e to the IB tilde and the unitary e to the minus IB tilde. Okay, even though these guys, e to the IB tilde and e to the IC tilde, don't commute. Okay, so now what is W? Well, here I wrote it in terms of the tildes, which are in the repertoire. But now let's write it in terms of B and C, which have the property that the commutator of B with C is precisely IA. So W is the identity minus, I've rewritten the commutator of B tilde with C tilde, is B plus order epsilon, commutator with C plus order epsilon. And then the higher order terms. I get the commutator of B with C, which is minus IA, and because of this minus sign, that becomes 1 plus IA. Everything else is of order epsilon to the 3/2. Okay, because I have a commutator of this order epsilon term with this order epsilon to the 1/2 term, and a commutator of this order epsilon to the 1/2 term with this order epsilon to the 1/2 term. Those are all of order epsilon to the 3/2. So W hits its target, which was e to the IA. Remember, e to the IA is what I'm calling U tilde inverse, up to an error, which is order epsilon to the 3/2. We did it. We managed to make the order, although it was order epsilon in the original repertoire, it's now order epsilon to the 3/2 in our repertoire constructed as, gates of size 4 from the original repertoire. That's what it took to get a good approximation to U tilde inverse. That took a circuit of size 4, but that means we have a circuit of size 5, W times U tilde, which gives me the approximation we were looking for to the target unitary with this error, which is of order epsilon to the 3/2. So that's how the claim works. Okay. And of course, since I made this remark before, but the new repertoire is also closed under inverse, because in R we had in the repertoire the inverses of all the elements. So any circuit that we can construct, in particular the circuits of size 5, the inverses of those circuits are also in the repertoire. If I take the inverse of W, for example, that's just going to be e to the IC, e to the IC tilde, e to the IB tilde, e to the I minus IB tilde, e to the minus IC tilde. So it's a similar string, but in a different order. And so since all four of these guys, e to the IB tilde, e to the IC tilde, e to the minus IB tilde, and e to the minus IC tilde, are in the original repertoire, we can construct W. We can also construct W inverse, and that shows that it works. So we've shown the claim, and then the recursive argument shows what I claim. This Solovay-Kitaev algorithm, once we found our epsilon net, where epsilon is small enough, I didn't tell you what the constant C is, but anyway, you see how the idea works. Now we have a method for constructing a circuit whose size is only a power of a logarithm of 1 over epsilon that approximates any target unitary to the error epsilon. Now, I didn't talk about the classical cost of finding this circuit. I only talked about the size of the quantum circuit. At least I didn't talk about it explicitly, but it was kind of implicit that it's not too hard, because the classical procedure is a recursive procedure. And each time, essentially, we do the same thing every time. So every time we have to call a circuit of size 5 to construct each one of the elements in that circuit of size 5. We construct them as circuits of size 5 the next level down, and those as circuits of size 5 the next level down. So in other words, each time we add a level to the hierarchy, we're increasing the classical complexity of the procedure of finding the circuit by just a constant factor. So the classical cost is exponential in K, just like the quantum circuit size is exponential in K. And that means when expressed in terms of epsilon, the classical cost of finding the circuit is a power of a log of 1 over epsilon as well. So we can find the circuit exponentially, and it's an efficient circuit with a size that only grows polylogarithmically in 1 over epsilon. It seems like a bit of a miracle that it could work, because we started out with gates which had an order epsilon error, and we built circuits out of them. And as we discussed in the last lecture, if you build a circuit out of gates, all of which have order epsilon, then you would expect the error to accumulate. So you'll have an error which is of order epsilon times the size of the circuit. That's not what happened here. We actually wound up with a smaller error for the circuit than for each one of the individual gates. How do we make that work? Well, it's because we were able to cancel the leading order epsilon error. And what made it possible to cancel it was that our gate set was closed under inverse. So we had a way of getting the leading errors to cancel, and the non-leading errors were larger than epsilon by some power of epsilon, namely 3/2. And so repeating that, we were able to get smaller and smaller errors quite rapidly at a relatively small cost and increased circuit size. So this is a very powerful result. It's very general. Let's say you want to run a quantum algorithm. You figured out how to construct the unitaries you need for the algorithm out of 2-qubit gates. But now I have a machine which can only do certain hardwired unitaries, maybe because it's a fault-tolerant machine, and to get fault tolerance, there are only certain unitaries that I can do with good accuracy. And I've got to figure out how to compile your circuit using my gate set, but it's not so bad. For each one of your 2-qubit unitaries, no matter what my gate set is, as long as it's universal, I'll be able to find a circuit of my gates that approximates the unitary that you want to some specified error. Now, if your circuit has size capital T, then I'm going to want the error per gate to scale like 1 over capital T. So I'm going to want to make that epsilon go like 1 over square root of T. But that only counts a polylog 1 over epsilon. That only costs us a polylog 1 over epsilon factor, or polylog T. So T becomes T times polylog T. It's not such a big deal to approximate the ideal circuit with the particular instruction set I have. Yeah, that number, which was log 5 over log 3 halves, it's about 4, a little less than 4. For some gate sets, we can do better. The Solovay-Kitaev argument works for any gate set, which is really nice. But for some gate sets, they have a really nice structure, which allows us to do better. In fact, there are cases known where I can get the approximation to work with a number of gates, which is just 1 power of logarithm, not 3.97 powers of logarithm of 1 over epsilon. And that's actually the best we can do, because remember, we had that argument just from counting circuits and counting the balls that we need to cover the unitary group. If we want to, it could be, SU4, the 2-qubit gates, I'm trying to cover them with little balls. The number of balls that I need is going to be exponential in 1 over epsilon. And the argument, essentially was the number of circuits grows exponentially with the circuit size. And if we want to be able to approximate any unitary, then we're going to have a circuit size which goes with the error like the log of a constant over the error epsilon. So for some fixed n, like in this case, I'm talking about n equals 4, to get better and better accuracy, I have to increase the circuit size like log 1 over epsilon if I want to get as close as you want to any unitary in the group. So that's actually necessary. So the fact that there actually are gate sets for which it's provable that log 1 over epsilon is enough, that's a very pleasing result. Okay, so that's pretty much what I want to say for quantum circuits. Finally, we will be ready to move to the discussion of applications of quantum algorithms. That's where we'll dig in at the next lecture. Of course, what we want to confront or say something about is the big zillion-dollar question about quantum computing. Is it really powerful? Does it have applications, in particular ones that the world cares about, practical applications that we can run efficiently on quantum computers, but which we can't run on classical computers, problems we can't solve efficiently with classical algorithms. From the complexity theory point of view, the question is it true that BQP, the decision problems we can solve with uniform quantum circuit families, really is strictly larger than BPP, the decision problems we can solve with uniform randomized classical circuit families? Well, we believe it's true. That's why I'm teaching this course. That's why I and many others are eagerly pursuing quantum computing. We think it's powerful. We think it can do things that we can't do otherwise. But we don't really know how to prove that, not from first principles. Complexity theory is hard to really prove that there aren't circuits that can perform certain tasks. That's not so easy. So how do we make the case that quantum computing is powerful? Well, I think the best argument we have is, well, first of all, we don't know how to simulate quantum computers efficiently for classical computers. We think it's not because we're dumb, that we haven't been smart enough to figure it out. We think it's just because it's very hard to do the simulation in general. But apart from that, we do know of some quantum algorithms that solve problems efficiently, which we don't know how to solve efficiently with the classical computer, though we can't prove it's impossible. Finding prime factors of large composite integers is one famous example. The other famous example is the task of simulating quantum systems, in particular, simulating how a many qubit quantum system evolves in time as governed by some physical Hamiltonian. So we'll talk about those applications. We'll also talk about a model in which we can make precise statements about speedups of quantum circuits over classical ones. These are called relativized speedups. The model is variously called the black box model, the oracle model, the query model. The idea is that we have some subroutine we can call, which does something, and we consider we compare sort of making use of that box classically and quantumly, where in the quantum case, we're able to make use of it on superpositions. And in the classical case, we're not. And then to measure complexity, we just ask how many times do we call that subroutine, or in the lingo, how many times do we query the box or query the oracle in order to solve the problem. In that context, we can make statements about a separation in that query complexity, the number of calls to the subroutine, between quantum and classical methods. And it's also interesting to make statements about polynomial speedups. That's not directly relevant to the question of BQP not equal to BPP, which says that there's a super polynomial separation, that there are things we can solve in quantum polynomial time that we can't solve in randomized classical polynomial time. An example of a polynomial speedup is a quadratic one, applications for which the quantum computer runs in a time which is the square root of the classical time. Although it's not directly relevant to separating BQP from BPP, it's interesting and something worth discussing. So we'll get to that too. So I think that's enough for today. Next time we will start talking about quantum computing. Maybe this lecture was a little short. Maybe I didn't give you your money's worth, but actually I think we're a little bit ahead of the game. We're at the end of lecture 12. And I've gone further than I had originally intended in the first 12 lectures. Maybe that's because I go a little too fast when I'm using these slides, although I'm trying to mitigate that. But anyway, I think we've done enough for now, and it'll be nice to start on a new topic fresh next time. So let's stop it here, and I hope I'll see you again soon next time. Thanks for coming again and listening to me drone on and on. I appreciate it. I hope you're having fun in the class. Be well, and I'll see you again soon. Bye-bye.